collector or any glass, and these evacuated, you can see the evacuated is around 55%. Now collectors are different. The collector behind the panel itself, behind on the sheet, the solar thermal, we may have direct type, serpentine, parallel serpentine, modified serpentine, oscillatory, spiral. As you can see here, these are the different types, different design. And still until today there are many new designs. Recently I published with my research group, a new hybrid design where we connect these two together. We started as example spiral, and then we went to direct, and this was used to improve the thermal efficiency. We can also use thermal energy, solar thermal in dryers, as example for drying fruits, or as example human dates and so, or for fishes and other let me say animals and so. So you can see here, this is the solar collector. It gets heated, air will be pulled here using a blower, okay, and then is go for chamber. We put here the product, as example dates to get it right. Also we can use solar thermal in what we call a solar cooler system. Solar cooler system is similar to this. It's similar to the air conditioner we have at home, but the difference here is we are using a thermal driven cooler process. How this happen? We capture the heat, we torque the heat, okay, and we use it here in what we call thermal driven to produce cool for the building. Okay, the idea is, you know, in air condition, simply we have gas and we circulate gas using a compressor, and the gas, when it follow through the pipes, which is from copper mainly, it gets cold, and the air blown by fan into these pipes and get cold air, let me say. What happened here is, because we are circulating at that in the AC, we circulate the gas, we need more current, more power, more energy to circulate the gas. Difficult, is not easy task. But what they did here, they tried to mix the gas with another fluid, okay, to make it let me say fluid, to make it fluid. Now after, when we want to rotate the fluid in the pipes, it's very simple. We use like water pump, which need less energy, very fraction of energy used in the air condition. Now we need to separate then the fluid into the gas and the other fluid, other part. What they did, they used the heat for separation, and we get the gas which follow through the pipe, which produce cool and so on. So this is the way it's available in the market. Many countries are using them, and it's now here available in Oman. Now for ENGG is just, I would like to mention that ENGG is defined to be the maximum amount of work that can be produced by a system or a flow of matter or energy to reach equilibrium with reference environment. When we deal with solar thermal, we need to do ENGG analysis to check the losses, where it happened, which location, what type of losses, and so on. Now application of solar thermal, it's used in domestic, in commercial and industrial. I listed here, you can see them. There's a wide range of application. Beside the benefit of using solar energy to heat water and use it for many applications, it's from the other side have a good impact on environment, because we are heating but not burning any fuel type. Now the solar cell have been mentioned before, you remember. I will talk now, also I just discussed the thermal part. Let's talk about what we call it photovoltaic thermal solar collectors. Now this is the future of solar energy. Frankly speaking, this is the future of solar energy. Soon or far we will see that there is no separate thermal collector or separate photovoltaic. We will have hybrid system. Now this is the cell. If we plot the IV characteristics as we discussed before, this is how it look like. Now when temperature increase of the cell, its voltage, as you can see here, the red one, decrease. And when voltage decrease, power decrease, energy decrease, efficiency decrease, everything decrease. Okay, we need to cool it. We have different way of cooling. We have passive, we have active. Okay, for cooling the PV here, we can cool it by using fins similar to the fins we just mentioned in vacuum-tube thermal collector, or phase change material. You may ask, what is phase change material? Phase change material is a material which capture massive or huge amount of energy and it can release it. Okay, or natural cooling by using fluids. Okay, and active, we can for this let me say fluid to follow using pumps. Okay, the fluid could be air, water, nano fluid, or any other type of fluid. These are the fins. We put them fins. Okay, we put them behind the cell to cool it, as you can see here. Okay, now the same thing for phase change. We put them behind. When we put them behind, what we come up with, we'll come up with what we call it photovoltaic thermal hybrid photovoltaic. It means this is photovoltaic and this is thermal collector at the same time. Okay, now imagine this is PV. What we do, we container insulator behind. Okay, it's like a container. Then we put pipes, as you can see here, pipes. We can impress these pipes in PCM. At the end, we want to capture the heat from the back of the panel to cool the cell itself. When we cool it, we improve the power, efficiency, and so on. Let me say, not the best option for us to have PV separate from thermal system. Combining them together, we will effectively use the area. We will produce more energy, electrical and thermal at the same time, and we improve the efficiency of the overall system. Definitely, if we talk about thermal, we have thermal efficiency for thermal collector and we have electrical, but we put them together, we will combine them so to come up with higher efficiency. Okay, now thermal efficiency can be calculated by calculating the heat. We have formula for heat. We have the solar insulation and the collector area, and this is another let me say formula used to calculate the heat beside the previous one, which is called Hotel-Wheeler equation, where we have here a heat removal factor. We can take it from the data sheet, collector also from the data sheet. Here we have the absorbed solar radiation. We have here the heat transfer coefficients. We can find this information in the data sheet. Okay, for electrical efficiency, we have either, we discussed it before, we can calculate the output to the input power, or we can use this formula, relative efficiency here, and this is the temperature coefficient, and these are the PV and reference temperature of the cell. Now, thermal photovoltaic thermal system could be classified based on the type of cooler into air-based cooling, water-based cooling, combined air and water. By the way, they started with air, then water, then the combined. Okay, concentrated cooling and the advanced design. Okay, now each one of them also have sub classification. As example, when we go for air, we have single pass, double pass, and for water we have tube and sheet, round tube, and so on. For concentrated, we have low, we have medium, and different one. And for advanced, these are the new technology. We have a heat pipe as example, refrigerated, PCM based, nano fluid, nano PCM based. Okay, and our research group actually, they invented this one, which is called nano fluid, nano PCM. Okay, they invented this one, and at that time, talking about 2017, our measurement show that this is the highest efficiency ever, and it's one kind of photovoltaic thermal. Now here, let me show you the improvement occurs when we use solar thermal. Here, let's assume we have air cooling or nanofluid cooling. By the way, we must ask, what is nanofluid? Nanoparticles, nano small particles, very thin particles, and nano, talking about nano, not micro. When we add them to water, we create what we call it nano fluid. What is the benefit of this? Is to enhance the thermal conductivity of these fluids. Now, if we check the thermal efficiency for these systems, we can see that increasing the mass flow rate, regardless if it's air or nano fluid, will increase the efficiency. Yes, definitely we will capture more heat. And if we compare here PV and air temperature, PV temperature and air temperature, we can see that PV temperature here, when we cool it, this is how much the cool effect. It reduces the temperature of the cell. Now here is a comparison of electrical efficiency. This is the conventional PV without cooling, and here with cooling, different with water-based, nanofluid, water and air, nano PCM, and so nanofluid and air. You can see the efficiency going up, both thermal and electrical. Both of them are going up. Now, as I mentioned, we have a flat plate thermal collector, we have photovoltaic. They separate the roof into two area, but when we combine them together, we got what we call it photovoltaic thermal. It's clear that photovoltaic thermal improve around double the yield coming from electrical side. Okay, and let's assume it in this way. If we have thermal collector which have 50 efficiency, and electrical efficiency of the PV is 7, then the PVT, or sometimes they write it in this way, PVT, the total efficiency is 56 because we add in them. This is our PV, okay, and this is the back of the PV. We put either pipes in this way, as you can see, in this way, in this way. These are different type of collector, direct, parallel, split. The idea is we touch them to the back of the panel, to the cell, and it gets heated because the cell is already heated by the sun. Okay, we try to flow the water here to cool the back of the panel, so we cool the cells. For nanoparticles, when we mix them, okay, there are some properties we need to check them. These are the physical properties of the nanofluid. We need to check also the density, viscosity, thermal analysis. Here you can see here we have different type of particles. Nanoparticles are different. Each one of them give different performance for the PVT. At the end, what we come up with, if we use grid connected as example, what we put the panel here, PVT. Now we generate electricity. We send it to through the part of it to the grid, and part of it to be used here for lighting, for TV and other application at home. So our electricity coming from here, the extra will go to the grid. We sell it, and at the same time we have heat coming here. We can use it at home, inside home here. These are some of my publications related to the system. I will try to send you some of them. This is the previous system I mentioned for grid thermal PVT. We executed by one my PhD student executed here. This is a PVT, the back of the panel here. As you can see here, these are the collector inside. The collector is square type, not cylinder type, and these are the data acquisition with sensors and meters, and then we generate electricity. We send it to the grid. At the same time, we collect the thermal energy. We use it inside. Okay. Now we need to check how the flow when it started. Okay, when we start the flow. Okay, the water flow or the nanofluid flow. We can see it started cold and then it get heated while it's flow through the collector. Okay, here you can see here different type of nanofluid or water type, and the mass flow rate is different. This is 0.14 or 0.17. Here, as you can see, IV characteristics. This is IV characteristics, IV, and this is PV. We sketch in this way. I put them here together. But see, when I use PVT water, PV with TIO nanoparticles or SIO nanoparticles or SIC, and we compare them for the same system, we can see for using water we got the maximum is 80.6 watt, while TIO give me 93, while SIO give me 86, and SIC give me 115. You see, we improve the power. We improve the power production because of the type of cooling. Different nanoparticles give me different, let me say, performance. If we go to the cost, You see here the blue one here, okay, this blue one, this area, it represents the total yield, okay, and the proper production with respect to time for 1 day. And when we cool it, we're using nano fluid, we can see that it get improved. The red one is the improvement occurred. This is extra power we generate, extra energy we generated, and we will sell it to get extra money. And if we come to the decrease in temperature, you can see this is the temperature. It's get reduced when we use nano fluid. As you can see here, this is the amount of reduction in temperature, which is accounted when, as I mentioned, when we reduce the temperature, we reduce the we increase the power energy efficiency of the cell. Now, some of our publications related to this, we designed this system. As you can see here, this is the serpentine, okay, it's going here in this way, zigzag. Water coming here cold, it's going from here hot. And as you can see here, these are the real one. Inside, we try to impress it in PCM, and not only PCM, nano PCM. We need to do some tests on these PCM to make sure that they are mixed correctly, their properties, what they are, viscosity, density, and so on, and different, let me say, percentage of nanoparticles used. Okay, here you can see different percentages, and when we mix it, the color, you can see it is changed. And try to take XRD test to see the homogeneity of the nanoparticles within the within the PCM and within the nanofluid. And this is how it look like the just a minute. This is the comparison between them. You see here, this is the temperature with time. Here, this is the time. You can see here that the highest one here is the PV temperature. When we use different coolers, air coolers or water cooler or nano fluid cooler or nano fluid PCM cooler or nano fluid nano PCM, we reduce the temperature much, and this is reflected positively on the performance. For thermal efficiency, this is comparison for PV cell cooled by water, and this is by water and PCM, and this is by water, nano fluid, nano PCM. You can see that this is the temperature increase, thermal efficiency increase sharply. Okay, this is the water type, this is the PCM water, and this is the nano fluid, nano PCM. The thermal efficiency improve significantly. Okay, now if we compare efficiency, PVT efficiency, the overall, it means adding electrical with thermal, we can see that it was 60 for water-based type, 674 for nanofluid-based type, 85 nano PCM nanofluid type. It seemed to be, this is the highest efficiency ever in 2017 reached experimentally from system. We compared at that time, we compare the thermal efficiency to overall efficiency and electrical efficiency. You can see here the red one is our system, our design system, which uses nano PCM nanofluid. Okay, and to see how long it takes from us to return our investment, which we call it payback period, you can see that here comparison between nanofluid, water, and conventional. For conventional, our return back here between 14 to 16 years. When we use water, it's reduced, it's become here around less than 12 years. When we use nanofluid, it's return here, talking about 8 years. So you see, this is the term when it's reduced. This means that the system is better and get better. These are some of my publications related to this system. I will stop here and we will continue next module. Thank you.